CFD, you always, okay, so with CFD, you always have to, look at, plan your case before you even start. That's the most important part of it. All of the other things you see, you can always find a way to work around it. You need to plan and your cases. That is why I keep asking you, what is the game plan? What is the game plan? We always need a game plan in CFD. So we've covered everything about the meshing process, and then we're able to, most of us, or most of you were able to generate the mesh yesterday. But then you started encountering a few issues. And the issue that you encountered, one of the issues you encountered was the fact that when you use Parafoam after you've generated your mesh, you couldn't actually do it. You couldn't open it with Parafoam. And one of the reasons for the reason for that is that your files, the names do not correspond. So if you go into your zero directory, you have certain files in there, your pressure and your velocity files in there. And those files need boundaries, the names of the boundaries. But in this case, you don't have those names. So Parafoam cannot continue. So you basically have to input those names in the boundary files. Now, we started with this case, and basically now we want to build up on it. And you've seen that I've given you the geometry parameters, and I've also told you that you have to use a velocity of 1 meters per second. And we are going to be assuming that the fluid there is water, but we can ignore that for now and then just proceed. Anyway, so if we proceed with this, you'd realize that we now need to define boundary conditions. We also need our initial conditions and fluid properties. And we have to monitor convergence. So how do we proceed? How do we do this? So for a pipe, for instance, any suggestions? Otieku,
Yes, please.
suggestions. You have a flow through a pipe. What what do we need? What would be the potential boundary and initial conditions?
So the initial conditions we would have, okay, the boundary conditions. I know that at the boundaries, the velocity would be zero, and then at
Which boundaries?
the how do I put this? The as the radius of the pipe at r is equal to, okay, as r is
At
equal
the
to
walls.
zero. Yes, at the wall, at r is equal to zero, would have the maximum velocity. Then when r is equal, or when we have the radius up to the wall, we'll have the velocity to be zero.
Hmm. Okay, well, this if this were fluid mechanics course, I would have asked you why, but let's not go there. And anyway, so at the walls, basically at the walls, you have a no slip condition because there you are basically saying the fluid near any wall is not supposed to move. It has to be equal to the velocity of the wall, which is not moving, so it's zero. If the wall was moving, then the fluid close to the wall would have to be equal to the velocity of the wall. So you need to take care of that. Anyway, so at the walls, you have the no slip condition. So we already have one condition there, no slip at the walls. And then now we need two more. We need to know what is happening at the inlets and the outlets, right? So
Yes.
we know the condition for the inlet we've been given, which is that it is 1 meters per second. And in this case, if we say it is uniform throughout at the inlet, it's uniform, then basically in our case, that means the Z component, because we've basically that's along the length of the pipe. The Z component is equal to 1, right? How about the outlet? What do we do? Anyway, so at the outlet, we let our numerical tool calculate it for us. But we need to tell it that at the outlet, it should, right at the outlet, the cells at the outlet should be equal to the cells adjacent to those the outlet layer, which is that if you have maybe 100 cells, the cells at the end, which is cell 100, should be equal to the velocity for cell 99. So in this case, we can set a zero gradient because the derivative at that point should be equal to 0. And so you'll be able to calculate any value that you have. So now you set those conditions. So now we have the conditions for the velocity. We also have another variable, which is the pressure, right? So does this apply to the pressure? Yes. But in the case of the pressure, typically, because we don't even have an equation for pressure, so what we have to do is we solve the Navier-Stokes equation, and then we use the continuity equation as the objective function. So you need to basically use that to constrain the pressure difference. So for the pressure, we can fix the outlet, for instance, to be equal to maybe atmospheric. And then we can then back calculate from there throughout the whole region. So basically, we are saying to the solver that, hey, come up with a pressure that makes sure that we are conserving, mass is conserved, and then only the difference between the ends, the pressure at the exit and then the pressure at the inlet should actually agree. So at the inlet, we will define the pressure. We are not going to define the pressure. The pressure gradient there should be zero. Zero gradient, yes. But then at the outlet, we are saying it's atmospheric. And if we are basically saying it is relative, then in that case, that would also be equal to 0. Anyway, so we need to define the fluid properties as well. And you can find those in the constant directory. So we also need to monitor convergence as well. Now, before we even proceed to looking at the various setups in there, before we proceed to look at the various setups, we need to also understand a few things, which is that most of the numerical schemes that we've talked, well, we haven't really gone into that, but then most of the numerical schemes in OpenFoam are actually implicit, which means that it doesn't really depend on the time steps, right? So you don't have this limiting condition. If you use an explicit scheme, for instance, numerical scheme, then you have to satisfy some stability criteria. But that aside, you still need some conditions, which is that your time steps shouldn't exceed some particular size. The ratio between your time step and your mesh size shouldn't exceed some particular values. And so that is basically the current number condition or CFL condition. And it's basically defined as the velocity, the velocity multiplying by the time step size over the size, the mesh size, or the step size. And typically, it should be less or equal to 1. In general, it should be less or equal to 1. But for safety, typically, I recommend that you have those conditions to be equal to 0.5. If you really want to play it safe, 0.5, and then you can actually calculate what should be your delta T here. What should be your delta T here? So instead of trying to guess it or do trial and error, you can use the CFL condition to obtain your delta T. Now then, the question that naturally arises, since I've told you this, is, okay, then what is my delta X? Or how do I obtain that? Well, to obtain that, if you remember, every single time or during parts of this discussion, we always check our mesh. So if you check your mesh, you would see that there are some minimum and maximum lengths in there along the way. So use one of those, the minimum or the maximum, to obtain as your delta X. and then you can calculate. Anyway, so if you know your velocity, inlet velocity, you know delta x, then you should be able to calculate the time step size that you need to ensure that things don't blow up during the simulation, things don't diverge. So with that, mostly set your CFL to be equal to 0.5 and then calculate it based on that. And you should be able to get it. Now, this particular manual calculation isn't really necessary if you are dealing with different solvers. There are some solvers, for instance, that allows you to be able to do this automatic adjustment of your current number. And so if you are dealing with more advanced solvers like PimpoFoam, PisoFoam, Interfoam, and all the others, you don't need to actually adjust this manually, the CFL condition. So these are basically some of the solvers here that I've listed. PisoFoam, which is a transient incompressible flow solver. And so adjustable current number is yes. IcoFoam, which we are mainly using throughout this conversation, no, you have to adjust it. And so to do that, you have to go into your control dict, and then you have to add these two things. So basically, you have to add this three, which is that adjustable time step. You're going to be saying yes. Do you want, and then you specify the maximum current number, which is 0.5. And then you are telling the solver to adjust delta t. And you are basically saying that the maximum you have here should be 1 to the power negative 3. And if you look at this, you will see that this and this delta t and this delta t are inconsistent, which shouldn't be the case. This is just for illustration. So this is basically for the icofoam that I just changed in there just to illustrate what you need to do. Anyway, so once we know our current number, we also need to decide which solver to use, because you can see that certain solvers are for laminar flow, others are for turbulent. Icofoam is for turbulent. So you need to know your Reynolds number, at least approximately. You need to know your Reynolds number in this case. So once you know your Reynolds number, you can choose your solver. And if you know your current number, you can actually choose set up the time step. Now, typically, once we move into the zero directory, we want to look at the velocity file. And so here, the dimensions are basically shown here. The first is kilogram, then you have length, you have time, and then you have temperature, you have mole, you have candela, I think, and I think ampere also. The rest, typically, I don't use because chemical engineering. Anyway, so you can find out those details, or I can actually share this with you later. So now you need to define your initial condition. So the initial condition is basically, for our case, I'm basically setting it up for the pipe case, should be uniform. And because it is the velocity file, it's a vector. So we need to consider the velocity components in the x, y, and z direction, which are all fixed to be 0. Now, the boundary field, which are your boundary conditions, you need to specify the inlet. And here we are saying it's 1 in the z direction. Remember that you have type. You need to specify the type of boundary condition. The type of boundary, is it fixed? It's a fixed value. And then you specify the value. Now, you do the same thing for the outlet as well. If you have a value for the outlet, you can specify it. If not, then we can basically call it a zero gradient, which I already explained. Now, you do the same thing for the pipe walls. The pipe wall, we are saying it is a no-slip condition, or you could basically say uniform. You can choose to call it fixed, and then the value to be 0, 0, 0, which is basically the same thing. But if your pipe wall, if the walls are moving, like we saw in the cavity case, then that boundary condition specifying the value would not be accurate. So you need to make sure that that value that you specify is equal to the velocity of the moving wall, if you have a moving wall. So you need to specify that. Anyway, so one thing you would notice if you actually check the patches, which is the polymesh boundary files that will be generated, is that the names or the type of patch should correspond to the type of patches you have here. If you do change that, if you change the patches, the patch type here, you need to go into those files, those cases and directories, and then change the boundary types as well for consistency. Anyway, so if we continue and then we just look at, well, I've already explained this, so we can just move on to the pressure. So in the case of pressure, it's basically the same thing, but note that the units are different. And here we have meters squared per second squared for the dimensions. And so that is basically telling us that we've normalized by the density. We are basically assuming that the density is constant. And so here, the difference here is that you have uniform, and since this is a scalar, this has to be 0. Only one value has to be specified. Now, suppose you don't know maybe what boundary conditions are available to you in OpenFoam. Then you can use the banana trick, which is that, or you can even use your name, provided your name is not part of OpenFoam keywords. So in this case, if you say put in banana, and then you first run icofoam, in our case, if you run icofoam, it will give you an error in the terminal. And basically, the error is saying, hey, I expected the name, the keyword uniform or non-uniform, but I found banana. So these are the options. And so if you specify that and you move on to the next stage, for instance, fixed value, and you decide, okay, well, I don't know what it's supposed to be, you can still substitute your banana there and see what happens. It will give you the various options and you can just continue. So it's really intuitive, and then so it helps you actually come up with whatever could apply, the keywords that could apply in your case. Okay, now one more thing that I would like to talk about, although we would be implementing it, is the post-processing. Once you obtain your solution, you need to at least monitor your residuals. You want to see whether or not your case is converging. And so to do that, you need to save log files, right? So you need to save log files for maybe your mesh and also for your solver output, which is already always printed out on the terminal. But if you save it into a log file, then we can use the utility called foamlog to actually plot the residuals. You could actually use pyfoamplot, a Python utility that could help you do that. There are a number of explanations online that you can find. But then if you go with the foamlog, for instance, then you basically have to type in foamlog and then the log name, the log file name, right? And that generates, the log directories. And so all you then have to do is to go type in new plot, and you can begin to basically plot some of these things with the following commands. We will try this thing out soon. Now, one more thing is that when setting up your case, you want to probably get some probes, or you want to get some values that are of interest to you. For instance, we are interested in maybe shear stress on the walls, for instance. So you would want to actually monitor some of those fields. You want velocity magnitudes, you want maybe velocity and all that at certain locations. You can add those functions into your control deck, and you should be able to get it after you are done. And you specify those intervals at which you want the controls to be written out, and that is it. So this is all there is to the running OpenFoam case files from end to end. So at this point, let's just try to at least see what happens. Because I know that telling you is different from actually doing it yourself. You start facing a number of issues. So let's look at some of those issues together. So first of all, let me just reset this, and then let me. So I already ran this, but let me clean it, and then we can rerun this case. Please type, yeah, follow me, and let's move on from here. Anyway, so I've cleaned this. So yeah, I've cleaned this, and so we have nothing. Now let's go to the zero directory. So I'm just going to go into the zero directory and go into make sure that we have the velocity. So 0. So this is my velocity file. So 0, and then nano, you open that with nano. So make sure that you have this. Make sure that the boundary, the names are actually set. So inlet, the type is fixed value, and then the value is uniform. And we are basically setting this to 001. The internal field is 000, and then the dimensions are 01, -1, 000. Do you have it?
The mine is a bit different. Instead of inlet, it's moving wall. So I wanted to change it to
Okay,
full.
so yeah, change that.
Okay,
Change from moving wall to inlet.
let's and then fixed wall to outlets.
Yes. And then the other one, front and back should be pipe, because that's the name we've
Okay,
given to those boundaries.
yes,
So
please.
if you have one thing here is if you have different names to your case files, your boundaries, you should make sure that the names match. Otherwise, OpenFoam cannot find it.
Okay.
Michael, how are you going? How is it going?
Yeah, hello. So I opened zero and it's
I can't hear you.
yeah, I opened the zero directory and it's empty.
Okay, so it's fine. So just you can copy, you can just go back there and just copy from whichever case file has some of those files, and then you can start.
Okay.
Yeah. If you have issues, don't you can ask your colleagues or your friends, or just let us know so we can both be on the same page. Anyway,
Please, so which one you open?
I can't hear you. It's not very clear.
In the zero directory, which
Directory.
one?
Yes. So we are dealing with the U, the velocity. So you can see it here. You should always be able to see it here. Are you done? Can we move on?
Yes, please. Yes, please.
Okay. Anyway, so we can do the same thing, but for P. Make sure that the objects are basically exactly the name you want. Okay, so to make sure that at least the banana trick works, let's see. So I'm going to end this. Yes, exit. So I'm going to say ICO. First, let me generate my mesh. Okay, check mesh. And if I generate my mesh and I want to actually check the mesh and basically write the output to a log file. So I'm going to call that T and mesh. I'm going to say T log mesh log. Okay. And so this is written into the mesh log file. And so here, if you want to know what values to use, then what you can do is look for the minimum and maximum values. Hold on. Minimum and maximum lengths. Okay, face area. So you can basically take the face area and take the square root of that, and that should give you the minimum area. But let's look at it. So it's the same thing written in here.
Look,
Yeah.
please can you go over how you save the check mesh details to
Okay.
yeah.
So here, so if you want to save anything in there, right, to maybe a case log file, you can just call it whatever. So check mesh, and then you remember the pipe. So pipe redirect the output T, which is that part of that output is here, and then you can call it mesh log or something.
Yes, please. Thank you.
Yeah. All right. Anyway, so once we are done with this, we can proceed. Now I want to use, okay, well, let's see our control dictionary. So let's just go CD system. Oh no, let's just nano system control it. Okay, well, don't mind what is down there for now. So you can see that our application is IcoFoam here. So that's what we'll be using. We are starting from time 0, from the start time, which is 0, and then we are ending at 20. But I think 20 is a bit too long. Let's make it 10. But typically, one thing I want you to take care of when you are running these cases is that you shouldn't run your simulations shorter than what you expect. Let's say you have a 20-meter long pipe and your velocity is 0.1 meters per second. You can calculate the duration it will take for you to be able to obtain the solution. So if your time is maybe shorter than, if your time is shorter than maybe the time it takes to complete one length of the pipe, then basically your solution is not converging. Although the numerical solution could converge, what you have hasn't actually run to the outlet. So just make sure that the time is long enough to cover from end to end based on your conditions as well. Anyway, so let me just put this as maybe 5 so that we can proceed from here. So IcoFoam. Well, before I go into IcoFoam, let's also check what's in the constant directory. So in the constant directory, we have the polymesh, which typically isn't there if you haven't generated a mesh. So it's your polymesh file directory gets generated once you generate your mesh. But then one thing you need to specify is the transport properties. So here you have the viscosity, you have thermal conductivities, you have densities, all of them have to be defined in the transport property file. So let's just look into this for this particular case. Make sure that so here we only have the viscosity, and then it is 0.01 meter squared per second. So it is the kinematic viscosity. You see it?
Yes, please.
Okay, now let's exit. And if you would like, later on, you should check the polymesh file and see what is in there. And you can try to understand what is happening there. So now let's just run IcoFoam. But I also want to save the log file. So I'm going to use a pipe T IcoFoam log. Great. I'm in the constant directory. Now you see what happened here. I got an error. And the error is telling me that they were expecting something for patch field type, and found banana. These are the valid options. So 0 gradient and all of that. But then we had fixed value, if you remember. So we have to go back to that file and correct it. So there are various options here. You can see fixed value, fixed profile, and all of those fixed mean. So depending on your case or the complexity of your case, you would have to use a different kind of patch type. So if you have maybe rotating objects like an impeller in there, then you may have to be using either cyclic or cyclic AMI. So those are some of the things to consider. Anyway, so let's go back and correct this issue. It is in the boundary, basically the pressure. So here, so my case is running. Who else? Who is having issues? Are we all here?
No.
Okay, good. Innocent. MEA. How is it going?
So I'm getting this error.
Okay, what error?
Let me project my screen.
Okay.
This was the command for saving it.
Let me see. We'll define primitive entry starting at key and value. Okay, your U file. So let's look at, go to U. Yeah, nano. Yes. System. Oh, okay, yeah, 0U. Yeah. Well defined. Show me the error again. Oh, let's see. Okay. Go back and let's see where you entered there. Yeah. Fixed value. Put a space between uniform and your value. And then try it out and let's see. No, T. You've missed out the T. TEE. Yes. So your current number is too high. So we've solved that issue. Now you know why your current number, why your thing is divergent, correct? So you need to reduce the step size. Go to your control dictionary. No, you can just open it directly as well, just like you did with the other cases. Nano editor. System, and then, no, system, and then control D. You have, no, go back, exit. You haven't spelled it correctly. Control, you've missed the L. Okay, so increase your steps, your step size there. So decrease it to maybe 0.01. No, not that one, not the end time, the delta T. 0.01. Yes. Control X. Yeah. You can just press arrow up key, and that should take you there. Yeah. No, yeah. Anyone else has issues?
No, please. I think
Okay.
my current number two was also high, so I just followed what Martin was doing.
Okay. Yeah, so that is it.
For me, my issue is about the values you put in the P and the U. I think you went quite fast, so I didn't get it.
Show me what you have. Share your screen.
Please, I joined with my phone, so I'm now joining to the laptop.
Okay, so then I think you can just talk to one of your colleagues later on, and then we can and then see what happens over there, so they can help you complete it. Has anyone finished simulating their case?
Mine is still running.
Yes,
Mm,
please.
okay, mine as well.
Mine is done.
Oh, nice. So then project your case and let's see. Okay. Are you simulating the pipe, or what are you simulating?
Yes, the pipe.
The pipe.
Yes.
And it's 20 meters long. Is that what it is?
Yes, yes.
It looks like your computer is better than mine. Anyway,
Doc,
yeah.
please, mine is still running. Could it be a value I choose? Because
Is
when I
it?
check the time, mine is still running. So I don't know if maybe I chose something or I specify something that's is making it
No,
still
no,
run.
no, no. Mine is also still running.
Oh,
So,
okay.
and I'm not running in parallel.
Oh, okay.
Yeah. And yeah, I
Um,
think after this, after some point, once your time reaches around 0.65, 0.7, it should pick up because the solution probably has converged.
oh, okay.
Yeah, so it should be picking up soon.
Yes, please.
Yeah. Anyway, so we can just wait till everyone has it and then we can proceed. So check the mesh. I think with what you did, with what you did. So let's proceed. Do you also have, do others have their solution? You don't have to type this in. So just hold on. All right, it's fine. So I'll go into Parafoam. So Parafoam, apply. And so now this is where you can actually do a lot of.
Doc, we can't see your screen.
Oh, I see. I forgot I wasn't sharing. Anyway, so can you see?
Yes.
Okay. So now let's go to Parafoam. So in Parafoam, we have this. This is my case, right? So this is where you would most likely spend a lot of time trying to at least understand and then get the necessary information out of it. So I'll just show you a little bit of it, and then you can spend more time trying to
Doc,
perfect your craft on this. Yeah?
since we're not seeing your screen, could you kindly take us to where you exited a new plot?
Oh, okay. So screen, can you see?
Yes, we can
Can
see
you
your
see?
screen. Yes.
Okay, so I only typed in Parafoam and I'm here. So this is what I originally had. And so I've changed from solid and surface. So if you change to solid surface, this is what you have. Now you can play around with this a bit. So if you take this out, right? And then you just say opacity. So you can make it opaque. You can do a lot of things with this. You see it. And then opacity. So this is what people actually use if you want to have the pipe and other things in there. So you can change the opacity, for instance, by basically searching it. I just searched it here. And you should be able to find it and you can adjust it. Anyway, let's move on. Now, one thing here is you want to know your velocity. Or okay, pressure. Let's take pressure for instance, and let's see what happens. Now, it appears that the pressure. Okay, let's. So let me use internal and take out outlet, and then apply. You can see. Can you? So the time step is changing, and we have that. But let me use pressure instead. So this is the pressure, and basically how it's changing from the inlet to the outlet, which is, if you look at this map, that's your pressure. And this is the velocity. You can always scale your stuff, which is you want to scale, you can set a range. Maybe for instance, you want 1, rescale it. So you can see the colors are different now. Now, if your mesh isn't good, you see that if our mesh could have been better, but you would see that this place looks diffuse. It's not very sharp. You see that the colors are diffuse. So that is what people call numerical diffusion. So your mesh actually dictates that. So it has to be sharper. If your mesh is fine and good enough, it has to be sharper to be able to capture stuff here. But let's proceed. Anyway, so now what can we do? Let's see whether you would see anything familiar here. So you can do a contour plot or contour plots throughout the pipe. But let's just do a contour plot for Okay, so this is one of them. You can change even this value. You can change it. So you see UX, which is what we have in the X direction, the X component of velocity. You can have the Z component, which is basically uniform. And you can have the Y component as well, which is exactly similar. Do you see it? Now, we could move on and check this and then try to look at the vectors. I'm calling it arrow, and I'm going to be decreasing the numbers. Magnitude. Okay. So let me just get a plane and then let me slice a plane. So I'm going to be slicing along the red plane. And I can show plane and don't show. Yeah, so you can see the velocity along magnitude along this plane. And this is something you'd expect because if you start plotting the values, if you plot these values along this plane, you see that it has to be parabolic shape, which is exactly what you know. You see it?
Yes, please.
Yeah. Anyway, so you could look at the pressure as well. This is uniform. And so you could test out a few things on the points. So just play around with it and see what happens. Anyway, now one thing I want you to be able to do is at least you should be able to plot the values along a line. So to do that here, plot over a line or you can plot over time, or you can just choose a probe location to plot. So if, let's say, we choose a probe location to plot, I want to plot this, for instance, I can just click on this and say apply, and that should plot some value. If I click another point, and if I change it to maybe some other value, for instance, and apply, you can see the values should change. But say 0 and maybe 1. So you would see that the values are different. So you can plot all of this and basically extract the data.
Doc, sorry, please, I'm not seeing your screen. I don't know if I'm the only one.
Can you see? Anyone else who can see?
I can see it.
Okay.
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 Okay, I think that's come now.
Okay. So basically, where did you miss up to?
Oh no, I'm actually following.
Okay.
It just
So
went off for a while.
okay. Anyway, so this is one of the things you could basically say, hey, let's define the plot over some particular line. So you can see that there is a line going from this side to this side, right? Do you see it?
Yes, please.
So we need to define 2 points. If we want to look at the value, if you truly want to see the values across this cross section, then we can define those 2 points, right? Let's start from the x. Let's say negative 0.2, for instance. We can always, and 0.2 halfway should be, let's see. So, well, this is what it's looking like. But let me see. Let me put 0 here. And instead of this, let me check this, the pipe, so we can see. Okay, fine. So let's just add plot over line for the pipe, right? And so we are saying this. So we are plotting it along this line. Can you see? So we are basically plotting along this line, right? What are we plotting? Let's apply. Do you see it? Does it look like something you've seen? Maybe let me enhance it. So that is pressure and velocity. So this is just velocity magnitude. I've unchecked. So this is velocity magnitude. You can see it here and it's showing here. Now, we can basically enhance the axis. So you can see that it follows that parabolic profile right here. Let's see. We don't need to show the line again. Yeah. So we have that parabolic velocity profile. You can enhance it if you want. But that's what I'm struggling with. Seem to have missed the memo. Oh yeah. So we can set that here. We can enhance that. Let's start from 0 to 0.2. Too big. Too big. Too big. And this is 0 to 2. So you can see that parabolic velocity profile that you normally see. And the maximum is 2. It's not up to 2, but then you can kind of see it here. So typically you can extract all of these data points at different locations. Do you see it? Are you able to do it? Is anyone else able to do it?
So, Doc, I think somewhere in the after the geometry was imported to Powerful, in one of the results, I didn't get it. So I just kept following what you're doing.
Oh, okay. And then 0 to 2 on the left. So this is our velocity profile. Let's just make it 0.2. So this is basically the velocity profile. You see it? Let me uncheck the other ones. That's your velocity magnitude that you are used to. So qualitatively, well, we've kind of calculated it. So you can export this and plot. So it's nothing new. It's everything you've known, but then developed or enhanced. That's all. Anyway, anyone has questions? Do you have questions? So if no questions, I'll end it here. And if you have any questions, let me know.
Okay, so I was thinking, So this was like the example we worked with. So there was a pipe
I can't hear
flowing in
you.
the pipe. Okay, okay, I
I
think
can't hear
my
you.
can you hear me now?
Yes, I can hear you.
Okay. So I was saying this one was for flowing in a pipe. So I was wondering, in a
Ye-
case where I had multiple pipes, so like something like a shell and tube heat exchanger
Yes.
with flow on both inside the pipe and outside the pipe.
Yes.
Uh,
So typically what I think you would have to do. So with shell and tube heat exchangers, for instance, off the top of my head, what you are going to be having is two fluids, right? One one is basically moving in there and they are going to be exchanging heat, right? So they will not be in contact with each other. So it's still going to be you are just going to have two different fluids on two different sides of the exchanger. That's all. Hello?
yes, so during the geometry creation phase,
Yes.
well, we divided. So we gon let if we think about maybe the easiest example of that will be maybe a pipe in pipe example. So we
Yes.
divided the region into multiple blocks.
Yes.
Then so
So
in that case, will we merge the face of the internal pipe?
no. So you wouldn't merge. So you merge everything else, but then you wouldn't merge the center. So you remember the fourth block, for instance, right? The fourth block in our example here. So you wouldn't merge this block.
Okay,
So in that case, you would basically merge all of this and then leave this one. And then since you've basically used an arc for this side, you have to use an arc for this as well. Do you get it?
yes,
Yeah, so then you would have that tube in tube.
okay.
Yeah.
So the inner pipe is basically another block, but just not
Yes, so
attached.
yes, just not attached as one. So think about the case where people did the simulations, the example that I gave, that this one, right? So it's
Yeah.
just going to be something like that, but not merged.
Okay.
Yeah. So you saw that we tried to merge the two regions, but in your case, you are not going to be merging those two regions.
Okay. So
Yeah.
because they share the same face. I'm wondering how would
Yes.
the boundary condition definition be like? Because we might have created some inlet, but I'm thinking because it's two fluids, if those two fluids have different conditions, how do I
Yes.
specify different boundary conditions for both the inner pipe and the outer?
Oh, don't overthink it. Just think of it as two different systems. The only thing that they are exchanging is heat, energy. That's it. So the outer part, the inner part of your wall is just going to be the same inner fluid. The outer part of your wall is going to have the outer fluid on it. So that is how you would have to look at it.
Okay. Okay, look, thank you.
Right. And by the way, you don't necessarily have to use block mesh to generate your mesh. You can generate your mesh in any of the CAD tools, but just save it as STL. And please investigate a little bit on this before when working on it. So you can just generate an STL file And that would be more of the next level, but we haven't been able to cover that. So what you would then do is use it in snappy hex mesh if you don't have a mesh generation tool. So that's what you would then use to generate your mesh if your geometry is really complex.
Okay, so kind of like import the geometry from one of these, maybe something like AutoCAD.
Yes. And
Okay.
then you can clean it up and then just generate your mesh from there and proceed. But you need to save it in I think STL format.
Okay.
Mm.
Please, does anyone else have a question? Or do anything? Okay, it looks like everyone is fine. So, Dr. Baggy, thank you very much for everything so far. It's been a wonderful experience. We've learned a lot, and we are going to try to do more with what you've given us so far. I think this is the last day, right? Is this the last day?
Yes.
Okay.
Yes, it is the last day.
Okay.
And
So,
yeah.
okay. So, thank you. Thanks everyone that has joined us so far and has made this a successful program. We look forward to more things
Oh,
in
thank
the
you.
future.
Anyway, yeah.
But,
Thanks everyone for
please, we will get the
Thank
slides.
you so
Someone
much,
asking a
Doc.
question.
Oh yeah, the slides. Someone is asking about the slides. Yes, I'll put them together and organize it properly and then share it with Martin so he can share with you. Now the reason for this small delay is that the initial slides I had planned out was actually quite different from what we ended up doing because initially I was thinking about going into more towards the development side where you basically have to write your own C++ programs to actually do some of these things, which is more of the next level after this. So I'll put this together and then share this file with you.
But are you going to organize the next level um, tutorial or
Well,
something?
we'll see. We'll see. We'll see. Hopefully, I get a time to put some of these things together.
Okay. I told you I had a peculiar problem, and I don't know whether we can um, interact after this to handle it. Whether you would have the
Hello.
time. So let's say